So let's begin. All right, so here we go. We have a couple more questions to do. Okay, so in a study to predict the selling price of homes, various factors such as square footage, the age of the home, and the number of bedrooms are used. This method also, allows the inclusion of multiple explanatory variables to see how they collectively impact the house price. Okay, a quantitative response. This is multiple regression. Multiple linear regression. Okay, we have house price. Okay. Then we have I'm gonna say square footage. Just put it like that so I can move the right along. Square footage. Okay. Age and number of bedrooms. Alright, so this is Q. All these are Q. Everything's Q. It's quantitative. Okay? This is quantitative. This is quantitative. And finally, this is quantitative. However, this is going to be the RV, the response variable. Look at me abbreviating. And these are all going to be EVs. Explanatory 1, explanatory 2, EV. What happened there? This is going to be EV. Okay. EV. And also, this is going to be my explanatory variable. The best way to visualize this data is just, we didn't give it a name, but really it's a scatter plot, but it's a matrix of scatter plots. So you can see all the relationships together. So technically, this situation, there are two hypotheses. We're going to only highlight one of them, right? So the first one is testing if all the regression coefficients are equal to 0. So that's saying, okay, fine. H0, the null hypothesis. This is the omnibus test. Beta 1, since there are 3 regression coefficients, we know for a fact that since there are 3 explanatory variables, there has to be 3 regression coefficients. So this is 1, this is 2, and this is 3, alright? And in terms of words, I'm just gonna, doesn't matter the order you put this in. This is crazy. So here, the null hypothesis, so null hypothesis is that the population regression coefficients for square footage, age, and number of bedrooms is equal to 0. Square footage, age, and number of bedrooms is equal to 0. Okay, whereas the alternative, at least one of the regression coefficients. Okay, the alternative hypothesis is that at least one of the regression coefficients is not equal to 0. I'm going to say 4 here just so I can have context. 4 all right, that's that. Good job. All right, so then here we can continue. Researchers compare the age of blood pressure levels across 2 groups of patients who are taking different hypertension medications. Each group consists of different individuals, and the variable of interest is quantitative. Okay. Oh, so this is 2 independent population means. We don't know if it's Welch's or pooled, but the reason why it's 2 independent population means because it's 2 groups of patients. 2 independent population means. Okay. And then this is going to be type of medicine, type of group, type of group. You can say type of medicine, that's the way it works as well. And then blood pressure. This is going to be quantitative. This is going to be categorical binary. And then finally, this is going to be explanatory EV. We're doing that now, I guess. Then this is going to be the RV, response variable. The box plot is a good way to actually visualize this information. Okay? And then the alternative, the null hypothesis is that the population means are the same for both. I'm going to do them. Can I do that? Does it work? Let's see. It doesn't let me do that. Null hypothesis. Oh, no. Where'd you go? Okay. The null hypothesis, okay, is that the population mean for both groups, population mean of blood pressure are the same for both groups. And then the alternative hypothesis, since nothing stated otherwise, is that one is greater than the other. I mean, they're not equal. Okay, copy this. Population mean and blood pressure are not the same. Are not the same. And then we write this in symbols. Okay. And that would be that mu 1 is equal to mu 2. So yeah, we don't have to. Versus the alternative is that mu 1 is not equal to mu 2. That's the alternative. Okay, great. Alright. Continue on. Last question of this particular series. Okay, then we can jump into something new. Okay, to test the effect of a dietary supplement on cholesterol, blood samples from patients are taken before and after the supplementation period. The same patients are involved in both time periods. Okay, this is telling us clearly what this is. Making the data paired. Okay, set it in quantitative for cholesterol. So here we have the paired t-test because they're being same individuals, both time points. We're looking at the variable of interest is going to be the difference in cholesterol levels. Okay, I could say before and after. I'm going to say before and after just so I can be before and after supplementation period. All right, and this is going to be quantitative. And there's no response variable. There's no explanatory variable. The best way to visualize this is the box plot again. Our favorites. State the null hypothesis. The mean. The population mean of the differences. Yes, that's right. The population mean of the differences is, or the population mean of the differences of cholesterol before and after supplementation period, because it's long, was going to copy and paste it here, is equal to 0. That's the null hypothesis. Null hypothesis. And then the alternative hypothesis would be the alternative hypothesis is that it's not equal to 0. Okay. Alright, so then here we have our null hypothesis and symbols would be mu d is equal to 0. And the alternative hypothesis would be that mu d does not equal 0. So I forgot to do this. That's good. All right. So that was a review. That was a lot. Let me know in the comments if that was worth it. Did y'all like that? Give me a thumbs up. Subscribe. Don't subscribe. It's okay. Here we're gonna do something quite different. This is gonna be a little. I'm hoping to be short. It's only 3 questions, but it's a new technique within simple linear regression that needs to be talked about, and it's transformations. So technically we did this in class, but we didn't necessarily I didn't emphasize the issue. I didn't show you the visualization either. But that's why you have to visualize your data, right? So here, the summary statistics for horsepower and miles per gallon. Here's the visualization. But there's an issue, and you can't. Do you see that this blue line, right? It's the linear line. It's the line of best fit. Great, fantastic. But there are some gaps. It seems as if like there's some type of curvature that's going on here, right? And that is not ideal. That is not good. We need a linear relationship, not a logarithmic relationship, right? And so here's our analysis. We could use this analysis, but I would argue it's better if we do some transformation. So what I'm arguing here, okay, I'm going to say it again. What I'm arguing here is that since we say that there's a gap towards the bottom and it seems as if there's some curvature in this, I'm going to apply the log-based transformation to my x, because the x has a range of values where we see some spaces, whereas the y, it doesn't necessarily. What I'm teaching here is the basis of what you can do. There are so many things that you can do, but this is just one of many. So this particular thing that we're going to do is to transform our explanatory variable. What we're going to do is transform our explanatory variable by utilizing the log-based 10 transformation. Okay? Just because we're on Zoom and all that jazz, I'm going to just do one small thing, okay? Just so I can tell you what, I'll give you more information about log-based 10. This is not in the original notes. I don't have room for this, but I'm still going to do it and say that I know that log wasn't taught well to me, but I think it's worth mentioning. I know it's not taught well to a lot of people either. So 10 raised to the second power is equal to 100. So these are exponents. And so when it comes to log bases, what it's doing, it's the inverse of exponents. So 2 is my x. 2 is my variable in this situation. So let me write it again. F of x is equal to 10 root x. All right. And so the inverse, if I were to inverse this, if I were to apply a log base 10 transformation, or utilize a log base 10, what I'm doing is I'm essentially taking this log and I'm saying that my base is specifying it as 10. Okay, stop doing what I wanted to do. Give me a second. Log. Okay, good. Then my variable is x. Okay. So now this is f of x. All right. So now these are inverses of each other. What I mean by that is that if I put 2 into this, I'm going to get 100. But if I plug in 100 into this, let me write that down. If I plug in 100 log base 10 of 100, guess what I'm going to get? I should get 2. Okay? So what I put into this function, I will end up getting out on this side. Okay? And what I get out on this function is what I had to put in. That's the definition of inverse. Slow that down. I'll watch a small video on inverses if you need to. But the bottom line, if you fast forward a little bit to this part of the video, sorry for the noise, okay? Wow. So if the primary purpose of the log base 10 transformation is to shrink the values, right? We're going from 100, not 100, the max, from 52 to 335. And so what I need to do, or what I would want to do, is apply a log base 10 transformation to make it be from, or at least to make the minimum value be, let's say 2 point something all the way to 2.5, 2.4. Okay, so note that I said it should be like 2.1 or maybe 1.8. That's what it is. From 1.8 all the way to 2 point something, because I want to reduce the space here. So that's what the log base 10 allows me to do. Look at my graph. It's from 1.8, 1.7 or so, all the way to 2.5. Okay, that's what I'm doing. So this looks more linear, and that primary reason for me doing this is to make it more linear. Okay, so that is our visualization, and now here is our analysis. Yeah. Okay, so here's the analysis in terms of the regression coefficients. So look at this. Okay, this is something you should know. This right here, equation negative 24.785, is a different equation from this, right? And then look, r squared is 0.624 for simple linear regression. When I do the log base 10, it's 0.72. Wow, look at that difference. Am I selling you on this regression model? I should be, because this model works better when I apply the log base 10 transformation. Okay, so the primary purpose of the log base 10 transformation in this situation, okay, I'm just going to put it right here, is to make the relationship between horsepower and miles per gallon more linear. Okay, there are other reasons to make the data look more symmetric, aka look be normal, or even to make it even across multiple groups. But you're watching this, you're taking this over the summer. We're getting what we can get in, right? So this is right here is one of the reasons why we would actually do a transformation, is to make it more linear. Okay, great, fantastic. How do you interpret the regression coefficients? Okay, come to find out, you can't interpret the slope. You can't interpret this. Okay, you can't. All right, so because, hold on. How come you can't interpret it, Dr. Williams? Because you can't have 0 horsepower, because you take the log base 10 transformation. You can't have 0 as your horsepower, so you can't interpret it. Okay? So then here, the only thing that we have to interpret is the slope. So the thing is, because you've performed a log base 10 transformation, watch this. The convention is that we lost our units of our explanatory variable, so we must divide this by 100 so that we can mention the increase or the change in our explanatory variable is changing the response variable in units of percents. So let me write that out so I can say make more sense. So as the log base 10 horsepower increases by 1 unit, not 1 unit, 1%, I got messed up there. 1%, the mouse, MPG, MPG decreases by 0.2478. That's me dividing the regression coefficient by 100. So as the log base 10 horsepower increases by 1%, the miles per gallon decreases by 0.24 on average. Okay, on average. All right, that's good. The next big thing to note, last question of the day. The next thing to note is what would be the miles per gallon if horsepower was 200? Use log base 10 transformation to it before you apply it to the regression model. What I mean by that, you'll see what I mean by that. But before we double check that, before we actually do this, we have to check if 200 is in between the min and the max, and 200 is between the min and max of horsepower. See the one I look at. I'm checking this one first, okay? So then, since it is, I'm going to do the following. I'm going to take the following equation. I'm going to do yi hat. We're almost done. Y I is equal to 72.64. Is it 64? 64. 72.64 minus 0. No, that's 0. It's not 0. It's 20. It's still 24. So when you're actually doing the calculation, you still use 24.7855 times log base 10. Now this is where it comes in. Log base 10 of 200. All right, I'm gonna run this into my software, and I'll get the answer. Let me pause the video. All right, so I got 15.6. Okay, that's that. Well, thank you for watching. Hopefully you made it this far. Good job.